Alright guys, so this is the video I promised you about the stuff that we are doing in chapter 12. I've already picked out a couple questions for us to do on differentiation, integration, and equation solving, because these are the ones that you would probably use the most as an engineer, and other ones are pretty basic stuff, like if you put in 4 variables and you have 5, it'll solve for the 5th one, right? But here we're doing equation solving. So this is the first question right here, and it is consider the following system of linear equations and use that for these 12.1 through 12.5. So we're not going to do the first part because the first part is doing it in the linear algebra way in the previous chapter, or not previous, but chapter 10. And we're going to focus mainly on how we're going to do it through symbolic equations, right, and symbolic variables. So we're going to go ahead and start. So I've already written in the equation set right here. And there's one thing I forgot before I typed it in because I was trying to type them in, is that there's one more thing you have to do. So for this to work, you have to you have to tell the MATLAB that there are symbolic variables. So I have to do SYMS, if you guys remember, X, Y, and Z, because these are the 3 variables that are in my equation. So that right there will make those symbolic variables. So now that they are symbolic variables, we can then do a solve, right? So I'm going to say answer is equal to, and then solve. So we need to solve equations, right? So the solve tool is the equation you are trying to solve. So you would type in equation A, B, and C here, right? And so if you hit run as the first equation here, let's see, there it is. So right here are our answers. So it says X, Y, and Z are one by one sim variables, right? And you could go and you could click on these and it would tell you the answers, and I'll prove it here, right here. Oh, it didn't actually. Never mind. I thought it would show it to you. So to actually show it, I know how you can show it. Oh, wait. Answer. Sorry. There it is. So if you go to the answer, that's what I meant to do. If you go to the answer and you go to X, Y, and Z and you double click on these variables, it will tell you the answer. So the answer for X is 844 over 239. But that's not really what we want, right? We want this to show up in the field, not through a bunch of other hoops that we have to jump through, right? So how do we do that? So there's a couple ways you can do this. You can do it through a structure array, which was something we did in the last chapter, but we didn't have homework over it, if you guys recall. What you can do is you can do the structure array syntax, which you would say is answer, which is our answer, dot x, and this will tell you the answer for x, which I'm going to do it up here in the command window, or the script window. So answer dot x, say answer dot y, and then answer dot z. And so what this is doing is it's taking this variable and it is telling you the answer. It's telling you one part of that for this variable. So x, y, and z. So this one should give us our final answers with all 3 of those. And it did. So right here, 844 over 239, which we already know was x, negative 406 over 238, and then negative 202 over 239 are x, y, and z respectively. But there's still one other way you can do this, right? You can specify their output names. So that's probably the preferred method of doing it. And what you should do is you would do this. You would do, instead of doing answer, which is what we did before, you would do brackets, right? Because if you recall, you can name the solutions, right? But it has to have the same dimensions as what you put in. So for example, you would put x, y, z inside brackets and set that equal to solve A, B, and C, right? And so what this should do is it should tell you each one's answer instead of, having to go through this other hoop. And if you do that, as you can see right here, it says x is equal to 844 over 239, just like it was last time. So all it did was give you the answer. So there's kind of 3 ways you can do an output here. You can do it through the structure syntax, which the structure array syntax, which is this. Or you can do it in a way that we've done previously before using specified output names. as x, y, and z. And we've done this through earlier chapters when we were making, I think, column names. So we've done this before, but this is the syntax you would use. Or you could just do it this way right here, and you would just have to go into answer and find your answer. So there's plenty of ways to do it, but obviously if you want to show your answer, you have to do this bottom part. And that right there was the first question. So essentially, the main things I want you to know from this is that by setting up the equations, you have to just put them in as something, as a variable of some type, and then you have to make sure that your variables are marked as symbolic variables. And then you just hit the solve button and you specify the equations, and that should solve them for you. And however you want to output, that's up to you. But if you want to see your output without having to go through these hoops, you have to do this. So that's the first question, right? So first question, done. Now, let's go ahead and move on. Let's move on to the next one. So the next one is something in differentiation, which I will move to now. So we're in calculus and differentiation, which is practice exercise 12.8. So it says here, it says find the first derivative with respect to x of the following expressions. So this would be x squared plus x plus 1, sine of x, tangent of x, natural log of x. So in this first one, these are all really easy, right? You know, this is 2x, 1, and 0, right? These go away, so 2x plus 1. And obviously this one's cosine. You guys can do these, right? But to actually do it through a solver, and by the way, there will be way more complicated ones than this, so you can use this as a tool to help you with more complicated ones, but these are just to show you how it works, and it'll work the same for those as well. So we need to do this one. So how do we do this one? Well, it says that we need to find the first derivative with respect to x. So how do we do it? Well, first we need to just do differentiate, right? So that's the function name. It's diff. So if you guys recall, this right here is the function for differential. And so for differential, you would just type this in. If you want the differential, put diff, and then inside of here, you just say your whatever you want. So this would be x squared plus x plus 1, right? And it will give you the answer whenever you run it. Although I'm going to stop these outputs because I don't need to see them anymore. So let's try that. So right here, you get the answer of 2x plus 1. So that is the differential, as I said before. And so you do this exact same one for all of them, which would be, you would say diff, and I think the second one was sine of x, right? And then you do another one, which would be diff tangent of x. And then we also have diff natural log of x, which would be log of x, right? So these are all the ones that we need to do for the question. So let's see what we get. All right, so log x. Let me see if it's capitals. Yeah, so it was a capitals. You have to be careful there. I put a capitals there. It's supposed to be a lowercase log. So this differential, the first one. So we'll start here. 2x plus 1. The second one, cosine of x, checks out. The third one is tan x squared, or tangent squared of x plus 1. And then we also have natural log of x, which is 1 over x, if anyone knows. So this right here is just how you would do a differential, right? But now we have some other questions as well. We have other ones to do next. So then we are going to do partial derivatives. So partial derivatives, if we go back to here, you guys probably haven't seen them yet. Or maybe some of you have that are in later maths. But essentially partial derivatives are their equations like this that have multiple variables in it. Like this one right here is, ax squared plus bx plus c, right? And so if you did this, what it's saying is that when it take the first partial derivative with respect to x, what you're doing is that you are taking the derivative of this right here, x squared and x, and you are treating all other variables as constants. That is what you are doing in a nutshell. So that is what we are going to do. So we have to make sure that we're doing this one correctly, right? Now, how do we do this one? So you can specify the variable in which you want to solve it for, but I'm not sure we're going to have to do that for this, but we'll see here in just a second. So the first thing we need to do is, since this equation has a, b, and c in it, we need to add that to our sims. So I'm actually going to do that now. So sims a, b, and c. And let me see if there's any other ones that I need to do. Looks like y. So y as well. So that right there will make sure that we have all these variables as symbolics, right? And I'm going to go ahead and run it just to be sure. Okay. So they should be in there as symbolics. Now, we have to do the answer here. So let's go ahead and see if it'll work the first way. So I'm going to do diff, and we're going to do the first one. The first one was ax squared plus bx plus c. Okay? So we have a times x squared plus b times x plus c. And if we diff that, we should, I'm going to see if it works first. Yes, I'm going to go ahead and block these from going as well. So you can see we have b plus 2ax is the answer. So that is the first partial derivative with respect to x. So now we have to do the other ones, right? So, let me see. 2a, is it 2ax? I'm making sure that that's right. It is. So how I know that it's right, though, is that if you did this partial derivative with respect to just x, you would go, okay, I take the a as a constant, so you put that on the outside. You would treat that as like a 1 or a 2, whatever it is. It'd be 2 goes down in front, you have a 1 up top, so it's 2ax right here. Then you slide over to b. You would do a derivative of x. Derivative of x is 1, so you just have b here, and then a derivative of a constant is 0. So that you would have 2ax plus b as your answer. So that one is right. Now, let's do the next one. So the next one would be, I think it says x to the 1/2 minus 3y. So let's go ahead and do this one. So diff x up 0.5 minus 3 times y. So let's see what that brings us. And I'll type the rest of them in as well, just so we can move along here. So let's do diff. And another one was tangent of x plus y. There. And then the last one was diff of 3 times x plus 4 times y minus 3xy. So times x times y. So this right here would be what you do. Okay? So now I'm going to see if these work. I'll stop that one for now. So it says that the answer for the this one right here, this first one, which is x to the 1/2 minus 3y, is 1 over 2 x to the 1/2. So it's essentially 1 over the square, 1 over 2 square root x is the answer. So 1 over 2 square root x, which is probably the more complicated one on here because it has to deal with the 1/2 powers. Essentially what happened is that you subtracted a 1 off of the x. Let me see if that's what it was. Yeah, you subtracted a 1 off of the x here, and it gets a negative 1/2 power. You bring that to the bottom since it's 1/2, so that's 1 over the square root of x. And then this goes away. 1 over 2 square root x, sorry, because then you multiply by it. Yeah, so that is right. Sorry. So now, the next one, let's move down. Tangent x plus y. I will not lie to you, I do not remember much about tangent derivatives, because it's been a very long time. But assumingly it is right, even though I typed it in. I don't know that for a fact, because I can't do this one. Or at least I could if I remembered the rules. How about that? But it's been a long time. But I'll move on to the next one and confirm that one. So this one's pretty easy. Obviously, 3 times x, if you take the derivative of this, you just get 3. This one right here goes away because 4 times y is treated as a constant, so 4 times a constant, a derivative is 0, right? And then this one right here, at the very last one, you take a derivative of x is 1, which means all you're left is 3y. So this should be 3 minus 3y, and it is. So that one, fairly straightforward. And then we're going to move on, and we are going to do this right here. Find the second derivative with respect to x for the following expressions. So the second derivative. So what you could have done here is, you could have done this a bit differently. You could have labeled these as actual variables. So I could have said, like, I don't know, GHI are equal to these, and then I could have done a differential of those. But instead, what I might have to do is you will have to take the second derivative of that. Or you could do it. There's like I said, there's a couple of ways you could do it, but the one that we talked about was if you just put diff and then you put diff again of what we have. So I'm just going to do I'll do the natural log one, which was log of x. And so what that was is it'll take the differential of log of x and then take the differential of that, which will be the second derivative. And if we do that, oh, did I miss a parenthesis? Yeah, I did actually. Did miss a parenthesis. And so you should get negative 1 over x squared, which is the differential of 1 over x squared. If anyone recalls that you go up a power on the bottom and you change the sign. So that one I know at least works right now. So 1 over x squared is correct for that differential. And so like I said, there's a couple ways you could have done it. You could have set these as variables. So like I could have just said like g is equal to this. And then I could have done down here, I could have gone differential of g. Because then g would have been equal to the differential of the first one. So like I said, there's ways you could have done this without that. Without having to type it in again, but that would have been something you could have done before thought. But there's one more thing I want to do. So there is also a way to specify what derivative you want to do. So the last bit here is I want to take one of these equations right here. So let's pick this one because it has y's and x's in it right here. So we are going to do that. So diff, and let's say we did this. 3 times x plus 4 times y minus 3 times x times y, okay? Let me see what we have done here. So I think this is the command. I do want to make sure before I go though. So I'm going to do this really fast. Let me see. Yes, so essentially what I have done here is that I have taken this right here, which I'm going to space these out so you guys can better see them. So what I have done here is that I have written the exact same equation as before, except I've specified what derivative to take to do it with respect to. How about that? So I did the partial derivative of y this time instead of x. And so this is how you can get multiple partial derivatives, right? You just specify the answer here. If you just type this in, so the reason why it chose x was because MATLAB always chooses x as the default variable. But if you specify y, it will take the derivative of this with respect to y. If you would have done it up here and you would have said diff this equation and put a, it would have taken the derivative of this with respect to a, right? So you can tell it what to take the derivative of, and this is really helpful because you will, I know in the future at least, partial derivatives, you take a lot of multiple respects. Like you'll take, dz, you'll do differential of z, y, and x of the equation. You will do all. And so this is a good way that you could check your answer pretty easily, is that you just type it in and you tell it what you're going to do, or what one you want to take the derivative of. And the last part of this section is the exact same thing, though. So right here it says just take the first derivative with respect to y of these. it's the same thing. You would just, so you would type these in right here, and you would just specify at the end, I want it with respect to y, and you would just do comma y, and it would tell you. So I'm not going to spend too much time on that. This is just the example I used here. But you could do any of these that have a y and an x into it, and you could just specify y, and you would get the answer. So that is differentiation. Now we are going to work on inverse differentiation, right? Which is integration, right? So, right here, we have integrate. So essentially what this is, which is funny because they've given us the exact same questions as before. So which means that we're now taking an integral of these right here, which is the inverse derivative for people who have not gotten there yet. So that is the squiggly line, the one that here, if anyone hasn't done it, it's the ones that look like this. And then you would say x squared plus x plus 1 dx, right? So that right there would be an integral of this equation plus 1 dx. So it would be this right here. And usually there's some bounds here, like from like 0 to 10 or something, which is how you fill in the numbers. But that's for your math teacher. Essentially, I'm teaching you how to do this on MATLAB. And so we will talk about bounds very simply later. But for right now, let's just worry about this. So how this works, by the way, is essentially it is just like the inverse of a derivative, right? So if you were to get x squared, right? If you were to get x squared as a number, right? So if you were to go back to get x squared, how would you do it? Well, so for the people who aren't, familiar with it, essentially if we had x squared here, and this was before the derivative, right? Or this is after the derivative. That means that ours has to go like this. So this is the way that integration is going to work here, is that we're going to get x to the third over 3. And the reason how I know this is because the following. Because if then we took a derivative of this, you would get this, 3x squared over 3, which cancels out 3, and you're left with x squared. So this is essentially how polynomial integration works. Is so for derivatives, you bring this one down, and then you leave what's up top, right? For integrals, you add 1 to the top here and divide by that number. For polynomials, so for like this, polynomials is like that. But for other things, there are special integrations so I don't know if we're going to have to do, I don't think you do anything by parts or anything in this class, or in this. I don't know if it does that. I'd have to look it up. But essentially, that is the way polynomial integration works. And so we'll get to that. So let me get rid of this. All right. So let's start with the first one. And what's funny is that, these are very familiar equations. We will be able to, we already have a little bit of knowledge about these. So let's go on here. So it's going to work very similar to the other ones that we did, right? So int is the command. So if we do int and we do x squared plus x plus 1, right? And then we are supposed to do the integral of sine of x, right? So int sine of x, that's c. And then same thing, int tan of x, right? And then if you do the integral of natural log of x, so this will be log of x, okay? So these are the ones that we are supposed to do. So I've already shown you, so this first one I can pretty quickly do, although I think you guys kind of know what it's going to be. It will be x to the third over 3, and then this one will be x squared over 2, and then the last one will just be x. So that should be the integration of the first one. So we'll see if I'm right, see if my 4 years removed from calculus tells me anything. Let's take a look. So first one, okay, so I know what it did. So what it did is that it actually, so it combined like terms. So my answer was how it was going to be in terms of, in like more general terms, because as you guys can see, x3 over 3 plus 2, or what is it, x squared over 2. What they did is that they got like terms. 2, man, really loving that today. X squared over 2, and then plus x. They got a like term, like they got common denominators of 6, which is why you get the 6 at the bottom here. So, but yes, their answer is the same as mine, just with a little more maneuvering, and they actually factored it out. They factored a 6 out at the top. So good for them. And then I know the second one is correct as well, because if you were to get sine, right? So like let's look at this. So if you take the derivative of sine, you get cosine. If you take the derivative of cosine, you get negative sine, right? If you take the derivative of negative sine, right, you should get negative cosine, right? And then if you take the derivative of negative cosine, you should get what? Sine of x. So that means what? If you did essentially right here, if you take the integral of this, it works back this way. And it got cosine of x as what I just said. And if you go and slide over here, you will notice that the answer is negative cosine of x. So we know that the integral worked out. And like I said, you can write these chains down and you will be able to figure it out for at least, what are these? Are these not hyperbolics, right? I don't remember what these are called specifically. But these are the, sine, cosine, tangent. I just don't remember what they're called. Maybe they are hyperbolic functions. I don't remember. But essentially, you can write these out for those, and you can find the answers by going backwards. And so that one I know is correct. And then we have the integral of tangent of x. So integral of tangent of x is a special integral, if I remember correctly. I think it follows this form right here. But I do not recall that one. I do remember doing it back then, but because I'm telling you, they get really, really complicated when you get into the higher maths. They get really complex. How many things end up there? And then the last one, the integral of log of x. This right here is also a form. So whenever you get to do this class, this is another one that is very common, the integral of log of x. So it's log of x minus x is the integral of this. So it's sort of like it's a blueprint. They always sort of follow this line. Now, are all integrals ever in formats where you can get something nice like these? No. There are ways that you maneuver the integral to get it to end up in one of these forms. That's the way of like substitution, and you manipulate the integral to try to get it to this. Or something like this. Or something like this. Because you know those integrals. So that's kind of the problem solving of integrals. And then we have, what was the last one? So that says integrate the following expressions with respect to x. So I've just done those. And then it says do these with respect to x. So those are more complex because obviously they have x's and y's in them. So I will do those really fast. So it says int, right? Let me pull these up on the other screen. So it says you do int, and you would do a times x squared, right? Plus b times x plus c, right? And then you would do the same thing for the other ones. So you do int x to the 0.5 minus 3 times y. And then int 3 times x plus 4 times y minus 3 times x times y. Okay. And integrals have some of the same principles as derivatives, where if something is not being taken with respect to, like the derivative, so all of these are being taken, or the integrals are being taken with respect to x. So all these other variables are going to be treated like constants. So keep that in mind for our answers. Let me go ahead and stop these from showing up. So our new answers will be these following three. I didn't put the last one in, the tangent one. Maybe I just didn't want to do the tangent one because I can't actually tell you if it's right or not because it's been a long time. So right here we have int of all of these, and because we're taking this with respect to x, we do not have to specify that the integration is by x, right? If it was by y, we would have to tell it. So now let's go ahead and run this. So these are the answers. So for this first one, you get ax cubed over 3, bx squared over 2, and c times x, which I can tell you that is 100% correct. Because if you look at this, it works the exact same way as the first one. Remember, this equation right here is the same as this one, just without a, b, and c. So if you take this right here, it's x cubed over 3. This is x squared over 2. And there is a 1 right in front of this c, right? Because it's 1c. And if you take the inverse derivative of a 1, you will get an x, which is why you get cx at the end. So it is just like this. So that one I can tell you is right. This one right here, so this would be x to, so this is one of those weird ones. I hate these. So essentially it would go x to the 0.5, right? So if you take the derivative of that, x to the 0.5, it ends up being this, or the antiderivative, sorry. You add 1 to the top, so you get x to the 3 over 2 divided by 3 over 2. But obviously that flips around to the top, so you get 2/3. Sorry, I used the highlighter for some reason. 2/3. And you can tell this is right because then if you multiply by this, so when you bring this down, if you tried to take a derivative of this, you'd bring this down, right? And what would happen? Well, you would cancel out the multiplication of the 2/3, and you would be left with x to the 1/2. So that's wow, pretty straightforward there. So this one I can tell you is right. So this would be 2x to the 3 over 2 divided by 3, and then this over here, remember, because this right here is just a constant, once again, there's a 1 right here, a 3 times 1 times y. When you do the derivative of a 1, you end up with x, or derivative of the 3. The 3 is there, so you do 3x. So it ends up being 3xy, which is this one right here. So that one works out. Easy, straightforward. And because, if anyone just doesn't know, like I said, you haven't gotten there yet, you can split these up by these signs. So you could do the integral of x to the 0.5 minus the integral of 3y. Or you could also just do it this way, because this right here, this sign, doesn't really change anything when it comes to like your operations. Because you can pull it apart, it doesn't really change anything, so you just have 3y here. And you can do these separately. So that's what I'm trying to say. You could do these separately inside of one integral or outside of it. It doesn't matter. Now, if there's like, obviously it goes back to order of operations and things, but if there's something like this on the bottom, it does affect it. And then, once again, we're at the tangent one. I can't tell you if that's right. But it's just showing you that these are working, right? I'm trying to prove it to you that these are working. They are working exactly how you want them to.